Alrighty, we're back. Took a little break, got a drink of water, ate a bagel. Now we're back. Okay, so I said in the last video that I was going to go right into modeling the standoffs and the other parts for the gearbox, but I realized I think it would be more valuable to go through more the process that I would follow in a season rather than what we did in the actual in-person class sessions. In the in-person class sessions, I just gave you guys the dimensions for the parts, and that was to save science time, give you guys more time to actually work on some modeling. But here, we're not tied to a hard and fast time thing, so I would like you guys to see exactly how we go about determining these dimensions and how that will look in an actual build season design session. So what we're going to do is we're actually going to download our off-the-shelf parts, at least a few of them. We're going to download the gears, we're going to download the bearings and the motor. We'll leave the fasteners and some other stuff that we're going to need. We're going to leave that until a little later. We're going to download that stuff. I'm going to show you guys how to import those. We're going to save them, set all the materials, and then we'll work on modeling the rest of the parts. So I'm going to go down here to Chrome, and I have VexPro's website up. It's vexrobotics.com/VexPro. And what we're going to do is we're going to start with the bearings. We're going to go up here to Hardware. We're going to go down to Bearings. And we're going to scroll all the way down. Well, not all the way down. We're going to click on CAD files here. Now, we want flanged bearings, so we're going to scroll down a little bit to flanged bearings. We're going to use 3/8 hex. That's for the intermediate cluster shaft that has those 2 gears on it. We're going to use 3/8 hex, 1 1/8 OD. This is how you get the size of the hole that the bearing goes in, and it's 5/16 of an inch overall width. So we're going to download that. Next, we need a 1/2 inch hex, also 1 1/8 inch OD, and 5/16 wide with flange. This is for the output shaft. Well, one end of the output shaft. We're going to download that, and you can see down here they're downloading. And these are step files, so we'll have to import them into Inventor and save them as actual Inventor files. And then down here a little farther, this is a 1/2 inch ID, 1 1/8 inch OD. This is not a hex bearing, it's a round bearing, which we're going to use for the back end of the output shaft. So download that as well. Next, we need to get our gears. We're going to scroll up, go to Motion, go down to Gears. We're going to start with the motor gear. So we're going to go to 32 DP gears right here. Click on that. Scroll down, go to CAD files, and it's going to be at the bottom under 32 DP motor gears. You can see here 12-tooth steel spur gear for the RS775 motor. We're going to download that. Then we're going to go back. Come on, here we go. Next, we need, actually, I'm sorry. Go back to 32 DP gears. There's one more 32 DP gear we need. So up here under 32 DP aluminum spur gears, we're going to pick this 60-tooth aluminum spur gear and download that as well. Forgot about that one. Okay, now go back twice for some reason. Then we need the 3/8 hex bore that's going to go on the intermediate cluster shaft. So that's going to be a 20 DP gear, 3/8 hex bore. Click on that. Go down to CAD files. This is going to be a 16-tooth gear, so it's going to be this guy right here. You could go for steel, but we're going to go for aluminum just because there's only one motor on there and it's not going to be a lot of torque. So click download. Now go back twice. Next, we're going to need the output gear, which is going to be a 1/2 inch hex, and it's going to be 20 DP as well. So we're going to go here, all the way down, CAD files. And it's going to be 1/2 inch hex bore aluminum gears. We don't want the steel, we want the aluminum. and it's going to be a 60-tooth gear. So we scroll down until we find it. Now there's going to be two. So there's 60-tooth aluminum spur gear, and there's 60-tooth aluminum spur gear with Versa keys. We want the one without the Versa keys because we're not using the Versa keys, and it's cheaper. So download that as well. Okay, so that's 7 files. We'll download some fasteners and stuff a little bit later. We need one more, so we're going to go up to Motors and Electronics and down to the 775 Pro motor. This is the motor we're going to be using on the gearbox. You can see I was talking about those tapped holes, and these are the little vents that those 1/4-inch holes in our plate are going to line up with, roughly. All right, go to CAD files, download the motor, and that should be it. We'll download the rest of the files a little later. Okay, so what I'm going to do is I'm going to come down here to Downloads. I'm going to right-click. I'm going to click Show in Folder, and I guess I already had that folder open, but I guess I'll just close it. Okay, what we're going to do is we're going to select these. I'm going to hold Shift, select all of them, right-click, cut, go to my CAD class Gearbox folder, just paste them all in here. Now, typically what I do during the season is I name these step files ahead of time, and I give them a name. Actually, if we go to CAD standard parts, this is the Google Drive that we store all of our season CAD on. So this has got all the stuff, and this is just kind of how we typically name. I typically have the CAD students name stuff something like this. There's some messiness associated with it, but I guess the best example is probably fasteners. Like, we name it descriptively. I'm not going to do that for the class just because it'll take a long time. There's no reason to make the video longer than it needs to be. So I'm just going to save all these files, the names they are, and we'll just deal with it. So going back to Inventor, we're going to go to Open. You can do Control-O if you want. You can do File, Open, or you can click this little folder button on the application frame. Okay, down here under Files of Type, we're going to click the drop down, and we're going to go to All Files, so it'll show stuff that's not just Inventor files. We want to show the step files as well. Okay, so we're going to start at the top. That's our 3/8 hex bearing. We're going to select that. My computer froze there for a second. We're going to pick that. We're going to click Open. Click OK to that dialog. Okay, now the way I have my template set up, and I think the way that we've been doing it in the class too, it creates this extra sketch. I just go and right-click on that and click Delete. We don't want the sketch. Okay, so there's a little bit of prep that has to be done for each one of these files. This is the model of the bearing. I want a work axis that goes through the middle of it because it makes it a little easier to constrain to shafts and stuff. So what I'm going to do is I'm going to click Axis. Right here we're on the 3D Model tab. I'm going to click Axis. I'm going to find a cylindrical surface on this. Well, I'm just going to use this cylindrical surface, and I'm just going to click. Okay, and it places this little orange line in the middle, and I use that orange line in assemblies to place constraints. Next, we need to set the material. So if we click the drop-down list up here where it says generic, scroll down until we get steel. Now Inventor does this really rough steel texture that just doesn't look good, and it's confusing when you're looking at it in assembly. So I typically reassign to something more polished. There's one that I like called semi-polished. Okay, and this looks more like what the gears, or I should say the bearings, bearings look like in real life. Alright, so I'm going to give this a save. Now, it didn't create the Inventor part until I clicked the Save button. So if I had closed out this part before I saved, I would have had to start that process over again. It does not create the Inventor file when you import it. It creates the Inventor file when you save it. So just keep that in mind. I'm going to close this because I don't need it anymore. I'm going to go back and open again. I'm going to go to the next one. We've already done this one, so we're going to do this one. Open. Okay. Wait for it to import. Click OK. Delete the extra sketch. place the center line. Change the oops, clicked on the wrong one. Change the material. Ooh, what's going on? That is strange. Let's go. Pick something else here. There we go. That was weird. Okay. Semi-polished. Yes. Okay. Now I'm going to give it a save. Close it. Open. Go to the next one. So you can do these pretty fast. Next one's this one. Open. I'm kind of trying to talk about what I'm doing just because it's not, you can't hear my mouse clicks. I was hoping the mic was going to pick up the mouse clicks so that you could know when I'm clicking, but it doesn't. In the screen cap software I'm working, I haven't figured out how to do like a little flash on the mouse when you do it. I'll figure that out later, but I'm kind of in a hurry to get these videos done. So, steel, semi-polished. Let's save. And the reason we're setting the material is so that we get a somewhat accurate weight. Now, if you really wanted to be accurate, obviously this bearing is modeled just as kind of a solid lump, right? And that's just because you don't need to model all the individual balls inside of the bearing. You don't need to model the inner race and the outer race. There's just no reason to do that. But that means that, you know, the real bearing is made of a couple different kinds of steel, and it's got some hollow. It's hollow basically, and so the weight's going to be slightly different. So if you really cared a lot about the realistic weight of the bearing, you'd want to go in and you'd want to set the material or the weight manually instead of letting Inventor do it calculate it automatically. You'd want to set it to whatever the bearing actually weighed. And I'll show you how to do that because we're going to have to do it for the motor. But the bearings are so light and the difference isn't that big that we don't care. Okay, so we just imported our gear. These are going to be a little bit different because, well, not this one's actually not because this is steel as well. I'll delete the sketch, place the center line, set the material to, oops, I said it wasn't aluminum, steel. Okay, I'm not going to change the appearance on this because this is pretty much the color that the gear actually is. It's kind of black. Give it a save. Okay, open. It's going to be the 16-tooth aluminum. Okay, so this one, a little different in terms of what we're going to do here for materials. So delete the sketch. Now, this one's a little weird, you know, because the hex, it's not round on the outside. The hex, obviously, I can't place this work axis on the hex, so I've got to find a cylindrical surface, right? And it doesn't matter what cylindrical surface it is as long as it's concentric with the center line of the gear. So I have a few options. First of all, the ends of the teeth happen to be a cylindrical surface. It looks like it's straight, but it is actually curved, and the center of that curve is the center line of the gear, okay? The other option is this, like, little hub, little boss on each side. That's a cylinder on the outside. So that's what I'm going to use, but it really doesn't matter what you choose. So as long as you get a center point, you're good to go. Okay, so now gear models from Vex come in with a color, right? You can see up here, you've got these numbers. It's the RGB value of the color of the gear, and it's not one of Inventor's materials, and it's not default like the bearings were. So normally when you pick a material, Inventor automatically changes the color. All right, but if there's already a color associated with the step file, Inventor won't do that. So I will get back to that in a second. I'll show you how to override the default color and get rid of the default color so Inventor can specify the color. So we're going to click this drop-down list. Now these bearings, or I'm sorry, I keep calling them bearings, gears. This gear is made of 7075 aluminum. Now this is 6061. Now typically when I'm modeling a robot, I just pick 6061 because it's close enough. That being said, 7075 is it is noticeably denser than 6061 aluminum. I think it's like 20% denser. So 7075 aluminum is quite a bit heavier than 6061. So if we go to there's these different libraries down here. I typically use the Inventor library just because it has a few basic materials, but if I'm doing something that needs other materials, there is this other material library, which I hardly ever use, but it does have a bunch of different kinds of aluminum, including 7075. Okay, so we want to get rid of the default color. So if you go over here to solid bodies and you click on the little arrow, okay, that expands it. Then you see where it says solid 1, right click on that, go down to properties, okay, and you get this dialog box. Now you need to do two things. So you're going to click this drop down box, you're going to scroll all the way up, click as part, and then you're going to click clear all overrides. Then you're going to click OK. Okay, and you'll notice all of a sudden Inventor automatically picked a appearance when we picked aluminum 7071. Now this is a pretty ugly color, and I don't like it, so we're going to change it. The coating that's on those gears makes them kind of beige. So actually the default color would have worked. You know, it's pretty close to what this was, but we're going to go ahead and change the color anyways, just so that you guys can get the practice. So we're going to save that, close it, go to the next one. And now all these gears are going to be the remaining gears are going to be the same material and the same color, just for simplicity. I think the 32 DP gears might be a slightly different color. I don't quite remember. So delete the sketch, place the work axis, set the material, change the override, set the material to beige, and save. Close that. Okay, we got one more gear. Open that. Click OK. Delete the sketch. Place the axis. Okay. Change the material. Expand that. Right click on solid 1. Go to properties. Go to as part. Check clear overrides. Click OK. Select the color we want. Save. Alright, now one last imported part. It's going to be the 775 Pro motor. So in this one, okay, I'm going to go ahead and set the material to steel because that's mostly what I'm actually going to go to the Inventor material library for this because I don't care about the alloy. The motor. Well, all right, let's look at this here for a second. The motor is modeled as a solid block. Now, in reality, the motor is not a solid block. There is empty space inside of the motor, and then in addition, there's a significant amount of other materials. There's a lot of plastic parts in the motor. There's a significant amount of copper in the motor because of the windings. There's different kinds of steel. You've got bearings that have empty space in them. So the bottom line is, modeling this as a solid lump of steel is not a good way to accurately represent the weight of the motor. So what we've done, we've selected the material. We're going to leave the appearance alone because it's nicely colored when it comes in from Vex, and it looks, you know, you've got the brass or copper connections there, and you know, so it looks nice. We're not going to change the coloring at all because I like the way it looks. But we do need to change the weight manually. We set to steel just for consistency, but we're going to have to manually override the weight to make it what we want. So what you do, I need to do a couple things here first, actually. Delete the sketch, and I'm going to place the centerline axis on this as well for constraints. Okay, so to manually override the weight, what we're going to do is go up here in the browser, right-click on the title of the part, the very top, go to iProperties, go to the Physical tab, and we're going to update. Okay, now if this was as modeled, a solid piece of steel, it would weigh 1.657 pounds mass. Now in reality, this motor is 0.8 pounds, according to Vex's website. I can pull that up, and I can go back to the website and go to weight. It says 0.8 pounds. So what I can do here is I can actually manually override this box and type in 0.8, right, and hit update again, and it will set this to that weight, right? And now it's manually overridden. It's going to stay this way. If I go in and update again, it's not going to change. Now, if I want to go back to the default weight, you just delete the text out of here and update again, and it'll go back to its automatically calculated weight. So you can flip back and forth if you need to. But 0.8 pounds is what we want. Update. Click OK. Okay, so now when this is put into an assembly, it'll show up as the correct weight. So we're going to save this, and we are done importing parts for now. Okay, so what we're going to do next is we're going to use some of the imported parts that we have available to us at the moment to start assembling. Okay, so what we're going to do is we're going to go up and click New, and we're going to go to standard.iam, which is the standard assembly template. We're going to click Create, and once it loads, we're going to be presented with a blank assembly. Okay, so we're going to go up and we're going to click Place. We got to place parts in here. We did this a couple weeks ago in the class, but I'm going to kind of go over the basics here again. I'm going to browse to my parts. I find it helpful to look at large icons because Inventor gives me a nice preview and shows me what the parts are. So we want to start with our plate. In the class about assemblies, we talked about grounding your parts, and the first part you place should typically be the one you ground. So we're going to select this part. We're going to click Open. I need to zoom out a little bit here. All right, now this part, I like this orientation. This orientation is fine, so I'm not going to rotate it. Now I'm going to right-click, and I'm going to click Place Grounded at Origin. Okay. Now this part's grounded. It can't move. Everything else in our assembly is going to be based on this plate. Now there's two plates in the gearbox that are going to be separated by a couple inches or something. So I'm going to just place another one down here, and they're kind of just, they're not really aligned. They're just kind of both in there, but we got two plates. Okay. So now I'm going to hit Escape. I'm done placing parts. Now this part can move around. This part cannot move around. This like weird highlighting thing, this is a setting that I have changed myself. It makes it a little more convenient to work, I've found. So when you select something, it won't look exactly like this, but don't worry about it. Okay. Now the big point that I wanted to make was we don't know the distance between these two plates. Okay, we don't have any way to know that right off the bat. Now we could sit down and maybe figure it out, but it's easiest for what we're doing here. We can kind of use Inventor to help us figure out how wide it needs to be. Excuse me. So we're going to start assembling. We're going to start assembling, and we're not going to know how far apart these two plates are. Right? We don't know how long the standoffs are. We don't know how much space we need. We're gonna make this as flat as we can, while still having room for all the components. So we're gonna start assembling, and we'll figure that out a little later. So we're gonna start by placing in our motor. Okay. Now we need to. I'm gonna rotate this to be a little bit more convenient. Remember, the rotations obey the right-hand rule. So positive 90 degrees around the y-axis. We'll rotate the motor like that. Now we want to roll the motor to make the two bolt holes, which you can see right there, horizontal. So we're going to do a rotation in the x-axis, and that flips the motor kind of upside down. Now you can see the origin right where my mouse is. It's up. The motor's really upside down. There's no reason that that's a problem, but just typically I just rotate it 2 more times to flip it upright. So the holes are still horizontal. But the origin is the way that makes more sense. There's no real reason for that. It's just what I do. Okay, so we click just anywhere, place that down, then I press the Escape key because I'm done. Okay, so now we're going to constrain it. So we need to do a couple things. So we want the center line of the motor, which is represented by this work axis that I created when we imported the part. We want that to be centered on this kind of medium-sized hole here. Okay, so what we're going to do is we're going to go up and click the Constraint tool. Okay, this dialog pops up. We're going to click the work axis, and then we're going to click the inside of this hole. Okay, and you'll notice the motor jumps and lines up with it. We'll click the Apply button. You can also hit Enter. Okay, so now if I lined my holes up correctly, I did those holes from memory, so we will see. Well, let me show you here. So I'm going to press the Escape key to get out of the Constraint tool. This motor can move in and out, and it can rotate. Okay, we want to prevent both of those things, so we need two more constraints. So we're going to line up one of these holes with one of the screw holes in the plate. Okay, so we're going to click Constraint. We're going to go in and select the inside of this cylindrical hole surface. Go in and select the inside of this hole surface. That'll line those two up. We're going to click Apply. Then we're going to click the front face of the motor. That's one constraint. Then we're going to click the front face of this motor. We're going to rotate around. We're going to click the back face of the plate. And we're going to click Apply. Okay, now if we escape out of the Constraint tool, we can't move the motor now, right? I'm clicking and dragging it, and it won't move. That's good. It's fully constrained. It's locked in place. Okay, so now there's a gear that goes on this shaft. So let's go up to Place, and let's get the gear, which is this guy here, and click Open. Okay, now the gear does have a back side, so you can see here, if I look at it from the side, you can see the little hub that's right there on the right side, the little bit that's sticking out beyond the gear teeth. That side faces the motor. Okay, and that just helps space the gear away from the motor a little bit. So we're going to place this down just anywhere. It's just floating in there. It's not attached to anything. We're going to press Escape because we're done placing components. Now we're going to constrain this to the motor shaft. So we're going to click the Constraint tool. We're going to click the work axis on the gear and then the work axis on the motor. And that will line those two work axes up. Okay, we're using the mate constraint, which is the default one. Click Apply. Okay, so now we have 2 degrees of freedom, is what they call it. The motor can move in and out, and it can rotate, just like the motor gear, the pinion, can rotate and move in and out, just like the motor could a minute ago. So the first of these is easy to solve. We go to the Constraint tool, we rotate around, we click some flat face at the back of the motor, and we click this surface here. Now this is a bushing, or maybe a bearing on this motor. I don't remember. But we don't want to press that all the way on, because when you press it on, if you press too hard, you can damage the bearing. So we want a small gap in between here, just a few thousandths of an inch. So I'm going to type in the offset box 0.01. That's 10 thousandths of an inch. And that just will make, it's hard to see, but it makes a small gap between these two surfaces here, which is more realistic. You don't have to do this. I mean, 10 thousandths of an inch isn't much, and this gear is going to be longer. You can kind of fudge gears side to side a little bit, especially in FRC, because you know, it doesn't matter that much. But I do that just for realism. Okay, now our gear can still spin, but we don't care. Okay, the motor shaft spins in real life. Obviously, there's no easy way to constrain this to stop it from spinning, and we just really don't need to. So I'm going to let it spin, and that'll be fine. That won't hurt anything. Okay, so now we're going to go ahead and put bearings in these holes, the top 2 holes. So I'm going to click Place, or actually what I'm going to do, I'm going to right-click and click Place Component here. You can do it that way as well. And then I'm going to find my 3/8 hex bearing, which is the one that goes up here. I'm going to open. So the flange needs to be on the inside of the gearbox, so I'm going to rotate once around the x-axis. Remember, it obeys the right-hand rule. I'm going to rotate once about the x-axis. Now that puts the flange facing in, so I'm just going to kind of place this in here, right? That's the direction it'll go in, that hole there that it's kind of lined up in the viewport. Now the other bearing on this plate over here in this hole oops, will be the other way around, right? The flange will also be in, so it needs to turn 180 degrees. So I'm going to rotate, well, I'll rotate by the Z-axis twice. That'll flip the bearing around. I'll place it down here. Then I'll press Escape to get out of that tool. All right, next I'm going to pick the Constraint tool. I'm going to pick the cylindrical surface of this bearing and the, oops, that's the wrong hole, the inside of this top hole here. Okay, line that up. Then I'm going to go to the other bearing and do this. Same thing, pick the cylindrical surface there and the cylindrical surface of the hole. So I need to be able to select the back side of this flange. And if I'm careful, I can get in here and kind of get like really finicky with it and zoom in and kind of be able to pick the back, right? But if I exit out of the Constraint tool, I can just click and drag and pull this out, pull the other one out, and that'll make it easier to grab. Then I can go back in the Constraint tool and continue constraining. Okay, so I'm going to pick the inside of the flange. I'm going to rotate, pick the front of the plate, click Apply, or press Enter. Click the back of this flange and the front of this plate, and press Enter. Okay, now same problem as with the gear, the bearings can spin. Okay, they can't move in and out, right, or side to side or up and down, whatever. They're constrained in the hole and on the plate, but they can spin. That's fine. Same deal with the gear up here. They spin in real life, and anyways, and there's just no reason to go to the work to constrain it. It just slows down your model, and obviously takes time to do it. So no reason to mess with that. So those are our bearings. So now we're going to, now there's a shaft that goes in here, right? There's a piece of 3/8 hex that shaft that goes in here, but we don't need the hex shaft in here to constrain the gears. So we're going to go ahead and place the gears for this cluster shaft in this assembly, and I'll show you exactly how that works. And this is a workflow that I would use during the season pretty typically. So I'm going to go to Place, and I'm going to grab the 62 32 DP gear, which is this guy. Place that down. I'm going to hit Escape. I'm going to go up and place another component before I start constraining. And I'm going to grab the 16 tooth 20 DP gear, place it down as well, and hit Escape. So now I'm going to go to the Constraint tool. You can also hit the C key on your keyboard for the Constraint tool if you want. So I'm going to pick the work axis there and connect it to the work axis there. So I'm lining, there's no shaft in there, right? But I'm lining the centers of the gear up with the centers of the bearing, which is the same thing. And I'm going to line the center of this gear up with the center of this bearing using the same method. And I'm just pressing the Enter key after I'm placing each of those constraints because I find it a lot faster. So I'm going to exit out of that with the Escape key, pull these out so I can get to the back. When I'm modeling typically and I'm going quickly, I don't move things when I'm constraining them. But for beginners, it's going to be easier if you guys do that, just because you won't have to struggle to find an angle that you can select the surfaces you need to select. So it's up to you. Once you get comfortable at it, do what works best for you. When you're modeling a really complicated assembly, you're going to want to find methods that cut down on time and mouse clicks as much as possible. So go back into the Constraint tool. I'm going to select the back of this gear. We're just going to butt this gear right up against the front of the bearing. And because of the design of the bearing and the design of the gear, we don't need to have any space between the bearing and the gear, kind of like we did up here. Also, there's no pressing, like this gear gets pressed on, so that's why I was concerned about that. But we can just butt this right up against the bearing and apply. Same thing with this gear. The way that we laid out this gearbox, all the gears are about the same width except for this gear up here, and I'll talk about that in a second. All the gears are the same width, so we can just butt this one right up against that one. Okay. Now, what's the next thing we're going to do is we're going to have a gear down here. So we need some bearings in here first. So let's go ahead and get those in there and get this last gear in there. And so let's go to Place, grab the last. Actually, I'm going to escape out of that. I want to do the bearings first. So we're going to have a round bearing, I'm going to rotate this correctly. The round bearing is going to go in this hole. Escape out, place component. I'm going to grab the 1/2 inch hex bearing, and I'm going to rotate it the other direction, and it's going to go in this hole here. Once again, flanges are going to face towards the inside of the gearbox. I think, let me open this. You can open by selecting the part, right-clicking, clicking open, and it'll open the part. No. I'm just looking at the appearance of this. It doesn't look right. I'm going to make sure I selected it. Okay, it's just something weird. Okay, anyways, I'm going to go to the Constraint tool, and I'm going to constrain these the same way that I constrain the other ones. Okay, and I'm just pressing enter between each of these. Now, I can't get to this one because it's kind of inside the plate, so I'm going to go ahead and pull these out. Go back to the Constraint tool. I'm going to press the C key to activate the Constraint tool this time. Get around, connect the flange to the front of that plate, or I should say the inside of that plate. Click the inside of the flange to this to the inside of that plate. Apply. Alright, I will explain the reason for this round bearing here and this hex bearing here in the next video. We're gonna get our last gear in here, then I'm gonna end this video, and we'll do more in the next one. So I'm gonna place a component. I'm gonna grab my 62 20 DP gear now, open that. That angle is fine. Escape out of that. Constrain tool. Now I'm going to use the center line here, the work axis, I should say, to the work axis of this bearing. Then I'm going to get in here and get this angle. We're going to attach this gear right to that bearing. Apply. Okay. This is where I guess we need to determine the overall size of this gearbox. Right now we can move this. Oh, I forgot some constraints. Okay, sorry about that. We've got a little more work to do. So we gotta line up these plates. I forgot to do that. So you know, this gear here is lined up with this plate, and this gear here is lined up with this plate. But once we line the plates up, those two will be in line. So let's go back up to constraint. Now we're going to use a flush constraint, right? Because what we want to do is line the edges of these plates up with each other. So we're going to click the flush, then we're going to click one plate, we're going to click the other plate, then we're going to click apply, then we're going to click the side of the plate, the side of the other plate, and click apply. Okay, now if we exit out of this, now it slides back and forth, but it's lined up perfectly, and you can kind of just push it right through other parts. There's no collision detection there, but that's fine. All right, so what we're going to do is if we slide this closer and closer together, you can see these two gears mesh like they're supposed to, and we can go all the way to there. We can go until this bearing touches this gear. Okay, and that's what we want to do. So we're going to pull this back out. We're going to go to the Constraint tool. We're going to constrain that bearing to the inside or the outside of that gear and hit apply. Okay, and this is going to be the overall size of our gearbox. I'm going to give this assembly a save. Normally you'd want to save more often than I did, but we're just going to do that. That's the name of the assembly, and save it. All right, that constraint that we just created in here is going to be temporary. I'll explain more about that in the next video. We're going to go ahead and end it here. I'm going to, in the next video, we will model the standoffs, we'll model the shafts, we'll finish the assembly, we'll put in all the finished parts, and then either in that video or probably a separate video, we'll go through and we'll put all the fasteners in. So thanks for watching. That's that.